So let me just get started. I have a few minutes now. And we'll get started on a generalization of the linear model, the sort of multivariate linear model, okay? And this is what it looks like. So why might we be interested in sort of this more general linear model? I mean, maybe the answer is kind of obvious, but you know, I could sort of talk about a lot of, we could talk about a lot of examples where, you know, we're primarily interested in the relationship between one particular x variable and our dependent or y variable. But there are other factors that might come into play that we need to account for in our analysis. So that's one very good reason to consider sort of this multivariate linear model as opposed to just the bivariate linear model. It could also be that we actually have many variables. We don't have any a priori notion about what x variables might be important predictors of y. So think back to the example of a firm trying to decide who to serve ads on that Moby Dick t-shirt to. Well, they might not have any sort of a priori reason to think, well, it's people who read XKCD who might buy this t-shirt. And what they would like to do is get sort of the web browsing behavior of lots and lots of people and see all kinds of websites that they visit, figure out which ones actually buy this t-shirt, and then use the results of that analysis to figure out who to serve ads to in the future. Okay? So that's another reason why we want to consider models that have lots of, potentially lots of regressors in them, not just one. Okay? So as I said before, the sort of notation we were using for the bivariate regression was just sort of not up to the task. It was kind of clunky, it was a little awkward, and it turns out that we can sort of all of the things that I can say about linear regression can be said much more elegantly using matrix notation. Okay? So what we're going to do, by the way, maybe I should take a show of hands. How many people are familiar with some basic matrix notation and linear algebra facts? Yes. Okay, so there might be a couple who aren't, but it seems like the vast majority of the class is. So I have put up on the website, also under resources, a separate handout, and I forget what it's called. Maybe it's called matrix notation, etc., or something like that. And basically, it goes through in greater detail than I'm going to do in lecture. It gives you both a primer for matrix notation and reminds you sort of definitions, matrix algebra, linear algebra kind of definitions, reminds you of those, but then also sort of goes through the linear regression stuff in more detail than I'm going to do in lecture. So you can look at those notes if you want. Okay, so this is a job for matrix notation. We don't have too much time, but I'll just get started here. So let's replace this whole parade of x's with a vector, a row vector, okay? And let's define a new x that's identically equal to 1, and that's called x sub 0, 1, okay? And the reason we do this is because sort of implicitly in the bivariate regression, we had beta naught times 1. We never had the 1 there, but we, sort of implicitly there was a 1 multiplying beta naught, and then we had beta 1 times x sub I. Well, here we want to explicitly have the 1 in that first spot so we can do everything in matrix notation, okay? And so let's replace this whole parade of x's with a row vector. And so for each observation, we have a vector of different measures, x naught up through x sub k for each observation. okay? And then let's also replace all of the betas that multiply all of these regressors by a vector, in this case a column vector, a k plus 1 by 1 column vector of parameters beta, okay? Okay, and then that lets us use a much more condensed notation for our multivariate linear model. And it's just y sub I equals x sub I beta plus epsilon sub I. Okay? So this is the model for each individual observation. And so we can go even further. And we can basically put all the observations into matrices or vectors and sort of compress our notation even further. Okay? So now let's let y, the entire set of observations on our outcome variable across our different observations, let's put that into a n by 1 column vector. And then let's put our errors also into an n by 1 column vector. And then let's take each one of these row vectors that I defined on the previous slide. So remember, for each observation, we had a row vector that was the measures of all of the x's for each observation. Let's stack those up and put those into an n by k plus 1 matrix. Okay? So remember, this column here is identically equal to 1. And then these, the second column on, are all measures of our explanatory variables x1 through xk. So one more slide and then we'll call it a day. Then when we have defined everything and sort of created that structure, we now can write the multivariate linear regression model or linear model as y equals x beta plus epsilon with all of those dimensions up there. Okay?